Hello everybody, I am Ilgiz Murzakhanov from Technical University of Denmark. I will present our work encoding dynamic security constraint AC-OPF to mix integer linear programs with neural networks. Power system security assessment is among the most fundamental functions of power system operators. The AC optimal power flow is an essential tool for cost-optimal and secure power system operation. The non-convex AC-OPF problem minimizes an objective function subject to steady-state operational constraints. For example, in the current work, we minimize the cost of the system generation for the intact system state. All inequality and equality constraints have to hold for the intact system state and each contingency in set C. The inequality constraints in equations 2 to 4 define minimum and maximum limits of active and reactive power injections and voltage magnitudes. The inequality constraint in 5 bounds the absolute apparent branch flow for each line. The equality constraint 6 enforces the AC power flow balance at each pass in the system. We consider preventive control for N-1 security defined in 7, so that generation active power set points and voltage set points remain fixed if a line outage occurs. While the obtained generation dispatch from the AC-OPF solution ensures compliance with static security criteria, the dispatch additionally needs to comply with dynamic security criteria, such as small signal stability. In 10, the term nu denotes the right-hand eigenvectors of the system matrix A. The term lambda denotes eigenvalues of matrix A, and gamma min is the minimum damping ratio. Note that the small signal stability constraints in 10 to 11 have to hold for each considered line outage in set C. Adding the small signal stability constraints increases the nonlinearity and computational complexity of the optimization problem substantially, so rendering it intractable and requiring iterative solution approaches. In the following, we introduce a framework which allows to directly approximate cost-optimal solutions. Using classification neural networks, we encode the feasible space of AC-OPF problem, including the mentioned static and dynamic security criteria. We train a classification neural network which takes the control variables U as input and predicts whether there exist state variables X such that the resulting operating point is in the feasible space or is indefeasible. Here we provide the general architecture of the classification neural network. For binary classification, based on a comparison of the magnitude of the neural network output, we can either classify the input as belonging to the first class, Z1 is greater or equal to Z2, or the second class, Z2 is greater than Z1. Here, the first class corresponds to the prediction that the input is in the feasible space, and the second class corresponds to the prediction that the input is not in the feasible space. The neural network is defined by a number k of fully connected hidden layers that each consists of nk number of neurons. A weight matrix W and bias B are applied between each layer. At the neurons of each hidden layer, the nonlinear ReLU activation function is applied. The ReLU activation function in 14 outputs 0 if the input is negative, otherwise it propagates the input. With the goal of using the trained neural network in an optimization framework, we first reformulate the maximal operator in 14 using binary variables bk. We introduce one binary variable for each neuron in the hidden layers of the neural network. In case the input to the neuron is smaller than 0, then the corresponding binary variable is 0, and the equations 15c and 15d constrain the neuron output to 0. Conversely, if the input to the neuron is greater or equal to 0, then the binary variable is 1, and equations 15a and 15b constrain the neuron output to the input. Based on exact mixed integer reformulation of the trained neural network, we can approximate solutions to the previously intractable problem by solving the following tractable optimization problem instead. The inequality constraint equations 17, 18 provide upper and lower bounds on the control variables. The exact mixed integer reformulation of the neural network is given in equation 20 to 23. The constraint on the neural network output in 24 ensures that the neural network predicts that the input belongs to the feasible space of the original intractable problem. The remaining nonlinear constraint in 19 enforces the nonlinear AC power flow balance for the intact system state only. While the number of optimization variables in equations 17 to 24 has been substantially reduced compared to the original problem, the resulting optimization problem is a mixed integer nonlinear problem, which are in general hard to solve. In the following, we will propose a systematic procedure to handle the nonlinear equality constraint in 19. The nonlinear AC power flow equations described by the nodal power balance can be summed over all buses. The summed active power balance of the system is as following. The first term is the sum of active power generation, and the second term is the sum of the active power loading of the system. The third term encapsulates the nonlinearity and represents the active power losses. We propose to use an iterative linear approximation of the third nonlinear term with a first-order Taylor expansion. The following notation is shorthand for evaluated at the operating point of the ith iteration. At the current operation point, we evaluate the value of the losses and gradients with respect to the active generator dispatch and the generator voltages respectively. Then we approximate the value of the losses as a function of both the active generation dispatch and the generator voltages using the first-order Taylor expansion. The iterative scheme has the following steps. To initialize, we linearize around a known operating point, for example, the solution to the AC-OPF. Then we solve the following mixed integer linear program for iteration I. By iteratively linearizing, we solve mixed integer linear problems instead of mixed integer nonlinear problems. Linear problems can be solved at a fraction of the time required for nonlinear problems. The classification neural network is trained on a finite number of data samples and with a finite number of neurons. As a result, there might be a mismatch between the prediction of the feasibility boundary and the actual true feasibility boundary. This could lead to falsely identifying an operating point as feasible while it is in fact not feasible. Adding the term epsilon to the right-hand side in 29 effectively shrinks the size of the predicted feasible space. This reduces the risk that operating points close to the feasibility boundary are falsely classified as feasible. We test our approach on IEEE 14-bus system. We require a minimum damping ratio of 3%. The control of variables are the set points of active generation and voltage magnitudes are fixed to the given values. We work with a balanced set of 36,000 data points. We split the data set into 80% training and 20% test sets. Our neural network has 3 hidden layers with 50 neurons in each. During training, we gradually increase the inference sparsity of the weight matrices to 70%. We evaluate the performance of our methodology for 125 random objective functions. Let's compare the solution to AC-OPF and N-1 security constraint AC-OPF with our proposed approach encoding the feasible space to mixed integer linear problems. Both the AC-OPF and N-1 security constraint AC-OPF do not return a feasible solution for 64.8% of the 125 random test instances. Following our proposed approach for a value of epsilon equal to 0, we decrease this share to 44%. Introducing a value of epsilon equal to 8 in the classification decision of the neural network allow us to obtain a feasible solutions for all test instances. The average cost increase of including N-1 security evaluates to 5.7%, and including small signal stability leads to an additional increase of 2.1%, which is expected. Notably, the additional cost increase by introducing a value of epsilon equal to 8 evaluates only to 0.5%, while it increases the share of feasible instances from 56 to 100%. On average, each MILP instance solves in 0.22 seconds for epsilon equal to 0 and 0.12 seconds for epsilon equal to 8, and is comparable for the computational time of 0.15 seconds of solving N-1 security constraint AC-OPF. Note that in terms of scalability, our proposed approach requires only to include the control variables of the intact system state and depends mainly on the tractability of the MILP reformulation of the neural network. The figure shows the share of feasible instances and the average objective value for epsilon ranging from 0 to 10. It can be noted that the average cost has a small linear increase, with epsilon reaching at most 0.7% increase for epsilon equal to 10. The share of feasible instances increases in two jumps from epsilon 2 to epsilon 3, from 56 to 81%, and from epsilon 7 to epsilon 8, from 82 to 100%. It can be observed that for epsilon equal to 3, true negative rate increases to 100%, which means that no infeasible sample in the full training and test dataset is classified falsely as feasible. To obtain a share of 100 feasible solutions with the 125 random objective function, the value of epsilon needs to be increased further to 8, resulting to a neural network accuracy of 93%. Using classification neural networks, we encode the feasible space of the AC-OPF problems, including any type of static and dynamic security criteria. Leveraging a mixed integer linear reformulation of the trained neural network and a systematic iterative procedure to include non-linear equality constraints, we accurately approximate cost-optimal solutions to the original intractable AC-OPF problems. We introduce a method to trade off conservativeness of the neural network prediction with cost optimality, ensuring feasibility of the obtained solutions. Considering both N-1 security and small signal stability and using an IEEE 14-bus system, we demonstrate how the proposed approach allows to obtain cost-optimal solutions which at the same time satisfy both static and dynamic security constraints. As an alternative to the proposed heuristic of identifying epsilon, our future work is directed towards robuster training of neural networks. Moreover, we look forward to investigate an efficient dataset creation methods of feasible and infeasible operating points, which at the same time describe the feasibility boundary in detail. Thank you for your attention.